DeepVisus, where vision meets depth. Episode: Beyond the Turing Limit. Can neural networks surpass computability? Hello and welcome to DeepVisus, where vision meets depth, and we venture beneath the surface of artificial intelligence, neuroscience, and the theory of mind to uncover what might just be the next frontier of understanding. Today, we explore a bold and brilliant book, one that doesn't just challenge traditional computing, but potentially rewrites its foundations. We're diving into neural networks and analog computation, Beyond the Turing Limit by Hava Siegelmann. And we begin with a question. Can analog neural networks do more than any Turing machine can? More provocatively, could the human brain itself be computing in ways that traditional machines, no matter how fast or complex, will never replicate? Let's set the stage. Alan Turing gave us the model of computation that still underpins all of modern computer science, the Turing machine. Everything your smartphone does, every line of code you've ever written or run, maps back, at some level, to this mathematical abstraction. It's the bedrock of digital logic and artificial intelligence. But Siegelmann asks us to reimagine this foundation. What happens if we step away from digital computers, those machines that crunch bits and operate with finite precision, and consider instead analog systems, particularly analog neural networks? Networks where weights are not rounded, quantized, or cut off after a few decimal places, but rather exist with real valued precision, just as quantities do in the physical world, or perhaps in our brains. In her groundbreaking work, Siegelmann proves something astonishing. Even small, finite recurrent neural networks, when supplied with real valued weights of infinite precision, can compute non-computable functions, problems that a Turing machine provably cannot solve. That includes infamous problems like the halting problem, a challenge Turing himself showed was undecidable. How is this possible? It's not about more memory or faster hardware. It's about precision. The key lies in how these analog networks represent and manipulate information. Where a Turing machine operates over discrete symbols with finite descriptions, Siegelmann's analog neural nets encode an infinite amount of information into their weights. These networks can be designed so that each weight carries Kolmogorov complexity, a measure of the algorithmic information content, allowing them to simulate oracle machines, non-uniform advice classes, and even access decision powers akin to entire hierarchies of complexity classes. In plain terms, these networks don't just compute faster. They compute what Turing machines can't, because they play by different rules. Siegelmann doesn't stop there. She connects this to dynamical systems theory, suggesting that computation in such analog networks is less like a series of step-by-step instructions and more like the evolution of a system through a continuous phase space. Every computation is a journey, a trajectory through state space, where inputs push the system toward attractors that correspond to the desired outputs. This opens a new paradigm, computing as physical movement, computation as a flow, not just a process. Now, think about the brain. Could biological neurons, evolved, noisy, analog structures, be operating in ways that digital models cannot capture? Could intelligence arise not from symbolic manipulation, but from continuous dynamics, sensitive to subtle variations in initial conditions and inputs? Siegelmann hints, yes, perhaps our brains, and the consciousness they produce, are leveraging forms of super Turing computation, not because we're faster, but because our wetware may tap into a different layer of computational physics. But let's be clear, this doesn't mean we should throw out Turing machines or digital computers. Rather, it means we've only just begun to understand the full landscape of what computation can be. It invites us to rethink the Church-Turing thesis, not as a law of nature, but as a model with limits. It nudges AI researchers to imagine architectures beyond the digital, to explore hybrid systems, neuromorphic hardware, and even quantum dynamical approaches. And it urges philosophers of mind to ask deeper questions. Are thoughts digital or analog? Is cognition just symbolic manipulation, or is it dynamical orchestration across a vast, continuous terrain? Conclusion. So, can analog neural networks go beyond the Turing limit? Yes, at least in theory. If we grant them infinite precision, if we embrace their analog nature, and if we open our minds to computing as a process of evolution, not merely execution, Then we step into a world beyond Turing. Siegelmann's book is more than a technical exploration. It's a philosophical challenge, a scientific hypothesis, and maybe, just maybe, a glimpse into how nature itself thinks. So stay curious, stay sharp, and join us next time on DeepVisus, where we'll continue our exploration into original and radical ideas, pushing the boundaries of artificial intelligence, the brain, and the mind. Because in this realm, depth isn't optional, it's essential. Until next time, this is DeepVisus, where vision meets depth.